Your liver is not waiting for dinner. It is already making a decision about what happens next. Store energy, release energy, or begin dismantling old cellular material for fuel. And if you are eating from the moment you wake up until the moment you sleep, that decision is being interrupted every few hours by a snack, a sweetened coffee, a soda, or a handful of calories you barely remember consuming. This is the hidden cost of constant eating. Your body may never fully leave storage mode. One meal a day sounds extreme because modern life has trained you to fear hunger. But biologically, the more important question is this: what happens inside your body when insulin finally falls low enough for your metabolism to change fuel systems? Hour by hour, your liver shifts gears. Your muscles alter how they handle glucose. Fat begins moving through your bloodstream. Your brain starts receiving a different chemical signal. But there is a point in this cycle where the body can either adapt or collect a biological tax. And that point is determined by what you do after the meal, during the fast, and especially during the night. The modern deception is simple. We believe that eating small amounts constantly is harmless because each individual snack looks harmless. A sweetened latte, a protein bar, a few chips, a sports drink, a late-night dessert. None of these seems like a major metabolic event, but your cells do not judge food by convenience, packaging, or portion size. They respond to hormones. When you eat, carbohydrates are broken down into glucose. The pancreas detects the rise and releases insulin. Insulin acts like a command signal. It tells muscle cells to take in glucose, tells the liver to store excess fuel, and tells fat tissue to reduce the release of stored fatty acids. That system is not defective. It is highly efficient. The problem is that most people activate it continuously. Humans evolved around an ancestral blueprint of movement, meals, scarcity, and recovery. There were periods when food was available, followed by periods when the digestive system was quiet and stored fuel had to be accessed. Modern life removes the quiet periods. You sit for hours, eat frequently, sleep irregularly, and often consume calories in liquid form. The result is an evolutionary mismatch. A body designed to switch between fuel states is trapped in a nearly permanent postprandial state. Postprandial simply means after eating. In that state, insulin is elevated, nutrients are entering circulation, and the body prioritizes storage and processing. That is useful after a meal. It becomes a problem when it never ends. A common belief says that eating once a day automatically slows your metabolism or forces your body into an emergency. The reality is more precise. The body does not panic the moment you stop eating. It begins managing fuel in stages. However, one meal a day is not magic. It does not erase poor food quality, chronic sleep deprivation, or excessive calories. It can also be inappropriate for people with certain medical conditions, a history of eating disorders, pregnancy, or medications that affect blood glucose. The mistake is treating fasting like a moral contest. The goal is not to suffer longer. The goal is to create a controlled period in which your metabolism can transition naturally from incoming fuel to stored fuel without turning the nervous system into an alarm siren. Because there is another modern deception. People blame fasting for the stress that was actually created by poor sleep, dehydration, aggressive caffeine use, or a massive meal eaten at midnight. The fast is not always the problem. Sometimes the problem is the metabolic chaos surrounding it. Now follow the sequence inside the body. Hour 0. The meal begins. As food enters the digestive tract, carbohydrates become glucose, proteins become amino acids, and fats are packaged for transport. Blood glucose rises. Insulin rises with it. Muscle cells respond by moving glucose transporters called GLUT4 toward the cell membrane. Think of GLUT4 as a series of doors that normally remain inside the cell. Insulin helps bring those doors to the surface, so glucose can enter. Movement creates another pathway. Muscle contraction can stimulate GLUT4 activity even when insulin is lower. This is why a short walk after eating changes the mechanical situation. Contracting muscles begin pulling glucose from the bloodstream without demanding the same insulin response. The liver acts like a central warehouse. It receives glucose and builds glycogen, a compact storage form made from linked glucose molecules. Some glycogen is stored in the liver for blood glucose regulation. More is stored in skeletal muscle for local use during movement. But glycogen storage is limited. Once the storage shelves begin filling, the body has to decide what to do with additional energy. Depending on total intake, activity, and individual physiology, excess energy can be directed toward fat storage. Hours 4 to 12, the first transition. As digestion slows and new nutrients stop arriving, insulin begins to decline. The liver detects that blood glucose must remain within a narrow range, because the brain, red blood cells, and other tissues still require fuel. The liver responds through hepatic glycogenolysis. That word describes the breakdown of liver glycogen into glucose. It is not a dramatic emergency. It is routine fuel management. The liver releases glucose into the bloodstream, while muscle glycogen remains largely reserved for the muscle itself. Picture the liver as a guarded power station. During the fed state, it stores electricity. As the incoming supply drops, it begins releasing power from its internal battery. At the same time, lower insulin removes part of the brake on lipolysis, the release of fatty acids from adipose tissue. Fat cells begin breaking stored triglycerides into fatty acids and glycerol. Fatty acids travel through the bloodstream and enter tissues capable of oxidizing them. This is where the metabolic switch becomes visible. Hours 8 to 16, fat oxidation increases. The exact timing varies. Your last meal, carbohydrate content, body composition, activity, sleep, and insulin sensitivity all influence the transition. But as glycogen availability falls and insulin remains lower, cells increasingly use fatty acids through beta-oxidation. Inside the mitochondria, fatty acids are broken into smaller units that feed energy-producing pathways. The mitochondria are not just microscopic batteries, they are chemical engines. They determine which fuel enters the system and how efficiently that fuel can be converted into usable energy. The liver also begins increasing ketone production when fatty acid delivery exceeds what it can immediately process through its standard pathways. One important ketone is beta-hydroxybutyrate, or BHB. BHB is not simply a backup fuel. It also functions as a signaling molecule. It can influence gene expression, oxidative stress pathways, and communication between tissues. The brain can use ketones, but the shift is gradual. One day of eating does not transform the brain into a permanently different machine. The important point is that the brain begins receiving a different mixture of fuel and metabolic signals. Hours 16 to 24, the conservation state. As nutrient availability remains lower, two major cellular sensors become more relevant: AMPK and mTORC1. AMPK responds to the cell's energy status. When energy is scarce, AMPK encourages energy production and conservation. It is like a circuit breaker that shuts down non-essential spending and redirects resources toward immediate survival.
mTORC1 is more active when nutrients and growth signals are abundant. When those signals decline, mTORC1 activity can decrease. This matters because nutrient sensing influences whether a cell prioritizes growth, construction, and storage, or maintenance and recycling. That brings us to cellular autophagy. Autophagy is often described as the body cleaning itself, but that phrase is incomplete. It is a regulated recycling system. Cells identify damaged or unnecessary components, enclose them, break them down, and reuse some of the raw materials. However, there is no scientifically confirmed human switch that flips at exactly 16 hours, 18 hours, or 24 hours. Autophagy is tissue-specific, influenced by energy balance, exercise, sleep, age, and disease state. The useful concept is not a magical timer. It is the gradual movement away from constant nutrient signaling. Modern eating can keep the cellular environment shouting, "Store, grow, process." A controlled fasting period may reduce that noise and increase the conditions associated with maintenance and energy conservation. But if you combine fasting with sleep deprivation, chronic stress, or a giant late-night meal, the nervous system may interpret the entire experiment as a threat. Cortisol rises. Hunger becomes more aggressive. Sleep quality deteriorates. The next meal becomes a binge. That is the biological tax, forcing a sophisticated system to solve problems created by your routine. The primitive protocol is simple. Move after eating. Stop constant snacking. Protect your sleep, and let insulin, lipolysis, and ketone production shift naturally. Step 1. The post-meal glucose walk. Within 15 minutes after your main meal, walk for 10 to 15 minutes. Not a sprint, not a punishment, just steady movement. Your target is a pace that raises body temperature slightly while allowing comfortable breathing. Each muscle contraction helps increase glucose uptake through GLUT4. This reduces the amount of glucose remaining in circulation and may reduce the size of the post-meal glucose rise. The walk is mechanical, not motivational. Your muscles become an active glucose sink. Step 2. End the eating window completely. After the meal, avoid grazing. No handful of nuts that becomes 3 handfuls. No sweetened coffee. No juice. No healthy smoothie. Water is appropriate according to thirst. Unsweetened tea or coffee may fit some people, but if caffeine increases anxiety, palpitations, or sleep disruption, it is not helping the protocol. Do not confuse stimulation with adaptation. Step 3. Use a 60-second nervous system reset. During the fasting period, perform 5 to 10 slow, comfortable breaths. Inhale gently through the nose if comfortable. Exhale slightly longer than you inhale. Do not hyperventilate. Do not force breath holds. The objective is not to chase dizziness or create a dramatic sensation. The objective is to reduce unnecessary sympathetic activation and support vagal tone. A fasting body does not need a second threat layered on top of it. Step 4. Protect the night. Finish the meal early enough that digestion is not competing with sleep. A massive meal immediately before bed can increase discomfort, body temperature, reflux, and sleep disruption. Aim for a consistent sleep schedule. Darkness, lower evening light, and reduced stimulation are not lifestyle decorations. They are metabolic instructions. Poor sleep can increase hunger signals, impair insulin sensitivity, and make the next fasting period feel much harder than it needs to be. Step 5. Do not train like a warrior during the adaptation phase. Avoid extreme intervals, long endurance sessions, or maximal lifting while experimenting with one meal a day, especially if you are new to fasting. Easy walking and normal daily movement are different from deliberately exhausting the body while underfed. If you experience fainting, confusion, severe weakness, chest pain, persistent vomiting, or symptoms of dangerously low blood glucose, stop. This is not a test of willpower. Step 6. Break the fast slowly. Take 20 to 30 minutes to eat. Start with protein, fiber, minimally processed carbohydrates if desired,
and nutrient-dense fats. Eat slowly enough to notice satiety before the stomach is overloaded. The first bite is not a trigger for a feeding frenzy. It is the beginning of another metabolic cycle. The protocol is not about worshiping hunger. It is about restoring contrast. Fed, then fasted. Storage, then mobilization. Stimulation, then recovery. That contrast is the signal your ancestral blueprint expects. One meal a day may reduce the constant insulin signaling, improve awareness of hunger, and give your metabolism a longer opportunity to access stored fuel. But solving the eating problem does not mean the system is fully repaired. Because the body has another blind spot, one that appears the moment you wake up. You can complete the fast, walk after dinner, and protect your sleep. Then, within seconds of opening your eyes, you can flood the nervous system with bright light, notifications, urgency, and information designed to keep you reactive. The same body that needed a quiet metabolic transition is suddenly placed into a neurological assault. The result is another evolutionary mismatch. Your liver may be switching fuel, but your brain is switching into threat detection.
And that is where the next biological tax begins. Before breakfast, before movement, before you even leave the bed. The most important question is no longer what you eat once a day. It is what your nervous system consumes in the first 60 seconds of the morning.